Propellers are noisy. For example, have you ever been going about your daily life at home only to hear the hum of your neighborhood peeping toms drone outside your window? If you haven't, then you soon will, because the future is now. But you know what isn't noisy? Cicada wings and owl wings. Cicadas do produce a lot of noise, but not from their wings. Their wings are actually really quiet, and it's their abdomens that create that buzzing noise. Owls and cicadas have a similar approach to reducing their wings' noise, and that is by having ridges along them. For owls, these ridges are on the leading and trailing edges, while for cicadas, they are along their entire forewings. So is it possible to use these features to make propellers quieter? And that is a little surprising in that owl wings and cicada wings operate at very different Reynolds numbers. The owl wings are at like 60,000, whereas cicada wings are about 2,000. The latter value is really small, and I don't even know if the flow there would be turbulent yet, even if they had ridges over their wings. It's just so low that the inertial forces are so much lower. And even more surprising is that apparently these ridges, which not only reduce noise on cicada wings, but also produce their aerodynamics, these ridges work at much higher Reynolds numbers too. So even though they do operate at 2,000, they have been shown to increase the drone's performance at higher Reynolds numbers too. So this natural flow control device is very robust. That naturally led these researchers to wonder if they could use these ridges to reduce the noise of propeller drones too. And to find out, they tested a few different propellers as shown in figure 1b. Here we go. This is 3b. There's also 1b, which they have other ones too. Here we go. And this paper here is called Towards Silent and Efficient Flight by Combining Bio-Inspired Owl Feather Serrations with Cicada Wing Geometry. And you can find this in the paper in the link below. So, for example, in figure 1b, let's zoom in a little bit here. We see that they tested all these different propellers, and they had a 6-inch diameter, which is about average. And they labeled them from B1 to B4, and one also called 3D-SC prototype. So let's go through each one of these ones just to talk about what they are. So first of all, the 3D-SC topology here is effectively a cicada wing just in a propeller form. So literally these are the same propeller, the cicada wing geometries. They just put them on propellers and they spin around. And I'm really interested to see if these work because as all animal wings are, they're designed to flap in some way. So the exact path that they take during the flapping motion is very different to this rotation motion. So will that result in similar effects or not? We'll have to see later. Anyway, the B1 propeller on the right here is exactly the same as the 3D-SC propeller, but it doesn't have these ridges. It's completely smooth. So the cicada wing planforms, but now they're just smooth. And by comparing this 3D-SC prototype with the B1 propeller, we can effectively determine what the effects of the ridges are on not only the propeller noise, but also the performance. So in addition to these two prototypes, they also have propellers B2 and B3. And again, for one, they have ridges and one without. And the B3 prototype is effectively just a conventional run-of-the-mill propeller on drones. It's not really anything fancy. It's not patented. It's just a generic propeller type. Now, they also tested the DJI propeller, which is this B4 prototype down here. And it's arguably the most popular consumer drone. I presume that one of these researchers had this drone that they use for peeping on their neighbors. That's what I assume. But anyway, they designated this propeller as B4, and they say that they use this one as an extra benchmark because of how popular it is, really. And I'm not sure how useful that is because when it comes to testing these ridges, there is no variation in another propeller. There's no B5 with these ridges, so we can't really tell the effect of these ridges on this particular propeller. But at least we can compare this propeller B4 with B3 and B1 just to see how these different platforms work. Now, one interesting thing is that they tested these particular propellers experimentally, but then they went further with CFD to see how changing the ridge sizes affected the sound, which we'll cover later on. Let's jump on to page 8 now, where they cover the fabrication method because this is quite interesting. So they had quite an extensive manufacturing process down here in here we go, fabrication. So to start off with, they 3D printed the propellers. The layer thickness was 32 microns, and 3D printing in general results in a very rough surface, and even tiny ridges can form. The authors understood that, so they sanded the surfaces down and then added an epoxy to stiffen the blades and then spray painted it. Now they acknowledged how this process could introduce some variability to the surface features, but they say that they use as thin layers as possible during the spray painting to hopefully not affect the ridges and hopefully not have pooling of paint elsewhere, which would then again change the performance of the propellers. And I think that this shouldn't be too much of an issue because there are two factors to consider here. The first is the surface roughness and the second is the size of the ridges. So for the surface roughness, apparently the Cicada ridges should work across a huge range of Reynolds numbers. That tells us that their benefits are a little insensitive to turbulence generation and propagation. As such, minor changes to the surface roughness shouldn't have much of an effect. As for the size of the ridges, well, in figure 1, they look pretty big, and even here as well in this figure. So I don't think that they should be affected too much by this minor finishing here. One way to glean whether this manufacturing process altered the propeller's performances is to see, hopefully later on, how the experimental results lined up with the CFD. If there is good agreement, then chances are that the manufacturing process was fine. And something that just popped into my head is how they mathematically describe the size of these ridges. So in this figure here, in figure 3 here, and figure 1a, there's a little cutout in the middle of the figure, in figure 1a. Here we go. Let's zoom in a little bit. And now they have a couple different labels. The way that they're describing the size of these ridges is actually the same way that you would describe something called tubercles. That's another flow control device. They used the letter A for the amplitude and the Greek letter lambda for the wavelength. And that tells us that these authors have probably read the work on tubercles concerning noise suppression. And this is originally done by Hansen and others, which you can find in the references. And this is a little tidbit which is amazing because tubercles are from humpback whales and these ridges are from cicadas. And tubercles, they have the ability to reduce the noise of an airfoil as well. And this actually came about from other testing. So what they told me was that the first author, Chrissy Hansen, was testing an airfoil with tubercles in the wind tunnel. And she noticed that it was quieter than the equivalent airfoil without tubercles. So that led to an experimental investigation where tubercles can reduce noise on airfoils, and she and they found that they did. And from what I can remember, I think that other people swooped in and patented the idea, and that's actually really common for tubercles. If you look at all the patents, most of them are by vultures, and fewer by the actual researchers who discovered the aerodynamic/hydrodynamic benefits. But the fact that tubercles, which are well inspired, and these ridges, which is cicada and owl inspired, show some level of convergent evolution. That is amazing just how different these applications are, but the geometries are so similar. Anyway, let's move away from this and onto the method. So to test these propellers experimentally, from their description down here, after the results, they align this paper quite unusually. But anyway, from their method, they used a typical test stand, which is literally just a pole for a propeller or a drone, a pole sticking up out of the ground, and then you attach the propeller to it, and there's a thrust meter in it. They also tested the sound coming out of it with a microphone with a sampling frequency of 48,000 hertz. So assuming that they used a Nyquist cutoff rate, that means that they could test up to 24,000 hertz in frequency, and that is just above human hearing. So they covered pretty much the entire range of human hearing. So for their CFD setup, on the right here, this computational simulations, the details they give are pretty slim pickings. I mean, they don't give any pictures for the setup of the mesh, or even their mesh. One good thing is that they used LES for the simulation, and they say that they had a cylindrical domain with the propeller in it, from what I can tell, and I think it's a sliding mesh for them, and then they had the outside part of that too, which was the general exterior. For their mesh, they say that they used 10 million cells for the sliding mesh region and an additional 2 million cells for the outside mesh. They say that most of these 10 million cells for the inside part, for the sliding mesh part, was used for the boundary layer mesh, the inflation layers. But there's no information about sizes or Y pluses. If you don't know what Y plus means, then check out this page on our website. But something interesting is that they say that the size of the domain was chosen by iteratively changing its size until convergence was achieved. At least that is how I'm interpreting what they're saying here. So what that means is that they did several simulations while changing the overall domain size, and presumably the sliding mesh size too. And then once they found the results, they didn't change with any further changes in size. Did they then conclude that the domain size was independent and they could use that one now? So personally, I'm not sure if this was the most efficient way of going about doing this. That's because there is so much research showing how far away from a wall a propeller needs to be to get no interference. So from memory, it's like 3 propeller diameters away from the sides of the sidewalls, and then like 5 diameters upstream and 10 diameters downstream from memory. There are a bunch of papers on it, but that's about right. So I imagine that a similar size would be required for CFD2. So you would need to go through this domain independent study. Now on the flip side, the authors here don't give a grid independent study, which is a little disappointing, especially because we're looking at aeroacoustics here. And for the sound part, the mesh is even more important than for the aerodynamics part. So I think that having the grid independent study would have been a good addition, and probably substituting that out instead of the domain independent study. So there isn't any validation either, from what I can tell, and that is really surprising to me because this is a Nature communication journal, and all nature journals are pretty high impact. So to have such a large omission is pretty surprising. Even in bad journals, these omissions are not really that acceptable. So anyway, on a different topic, if you want to learn how to do OpenFOAM and CFD thoroughly, then take our course in the link below. And anyway, let's jump into the results because the experimental data can definitely be trusted here. As for the CFD, well, I guess we will just have to look at the general trends and not anything exact, because without the validation and even the grid independent study, I'm not sure how accurate the exact values are. So let's jump on to the experimental results, and this is in figure 2 now. We see the various findings, and there's a lot of data here. It's really cool. Let's zoom into, here we go, for figure 2b. This is pretty good here. Okay, so we see something called the OASPL, which stands for overall sound pressure level. In other words, just how loud these propellers are generally. Not any tones, not any broadband, just all together. And the x-axis is for the amount of thrust the propellers are producing at any point, and the y-axis is this OASPL in decibels. Now remember that the 3DSC is the propeller with the cicada wings, and the ridges running along the entire way. And then B1 is the exact same propeller, but without any ridges. Then B2 is the generic propeller. Let's zoom, go across a bit. B2 is the generic propeller style with the ridges. And then B3 is the exact same propeller, but without the ridges. Then B4 is the DJI propeller, just added, just because. So the results are incredible. So for the 3DSC, which is the pink dots, and then B1, the prop, which is the yellow dots, and then we can see that across the thrust range from like, I don't know, maybe 10 grams force to 50 grams force, there's a drop in the overall sound by 7 or 8 decibels by the ridges. So the pink is lower than the yellow. The same thing occurs for the B2 and B3 propellers. The ridges, again, B2, are dropping the sound by like 7 or 8 decibels. That's huge. And what's even more surprising is how sensitive this benefit is to the blade profiles and even the thrust produced. It pretty much stays constant. I mean, the B1 was a Cicada airfoil, and B3 is a common propeller. Yet, despite being so different, they give pretty much the same general results. And this is the experimental data, which is pretty good. And they have the error bars here too, which show that the results are outside the errors. So that's really good. So that just goes to show how effective these ridges are. And it seems like you could pretty much slap them on anything and reduce the noise. Slap them on a Coke bottle and you'll be good. So for figure 2C, which is to the right here, we again have the sound pressure level in decibels, but this time we get the data from around the propeller. So a 360-degree circle. And overall, the sound is fairly omnidirectional, so no matter where you stand around the propeller, you're getting about the same loudness. And again, here, the ridges are reducing the noise by almost 10 decibels in pretty much any direction. So something that is interesting is that for figure 2b, we see the error bars, just here, but then we don't really see them in figure 2c. I'm not sure why or how the error bars are calculated in figure 2b. They say that they use a standard deviation of the microphones and then calculated the maximum coefficient of variation. So I assume that is what they're using for the error bars in figure 2b. If so, then I guess that means it's a 68% confidence interval, and that's a lot of information missing about the error bar analysis, but still, let's move on. Let's go on to the sound pressure levels in figure 2d, the spectrums. So the ridges are clearly, so I should mention that this is for the frequency from 0 Hertz up to 20,000 Hertz. And in the y-axis, we have the sound pressure level in decibels. And again, clearly the ridges are reducing the noise again, but they're not doing it uniformly over the entire spectrum, at least not for the Cicada propeller, which is the pink line here. The peak is reduced by the cicada ridges, but not as much as the broad spectrum frequencies. So you can see that, for example, at other frequencies, drops of around 15 decibels are seen between the pink and the yellow lines. But at the peak of 7,000 hertz or so the tonal frequency there, the drop is only maybe about 5 decibels or so. And the cause of this peak frequency isn't obvious here. I think it's to do with the blade tip, but maybe the CFD will show us later. So for the B2 and B3 propellers, which are the generic propeller profiles, and they correspond to the green and blue dots respectively, colors, we see that there seems to be more reduction of that peak frequency with this generic propeller when you put these ridges on. So maybe the differences in the flow fields and the CFD will elucidate why the ridges benefit the generic propeller more here than the cicada wings. In addition to that, the noise of the propellers reduced with these ridges, but what about the efficiency of the propeller in other ways? So for example, the thrust and the mechanical power used at different RPMs. So the more thrust you can produce at a given RPM, generally speaking, the more efficient the propeller will be at doing just that. So this data is given in figure 2e, and honestly, I can't really tell much of a difference, at least for the thrust. I mean, sure, there are some minor differences in this left figure here, some tiny differences. For example, for the generic propeller, which is for the blue here and the green, there seems to be a slightly more, a higher thrust value across the spectrum, but I'm not exactly sure what the error bars are. They say that the standard deviation is between 0.29 grams force and 0.66 grams force, which I guess would make up much of the difference seen here. So I guess we can conclude that the cicada ridges don't really affect the thrust produced that much. That's not a bad thing, because at least we still get noise reduction with no thrust penalty. Another measure of the propeller's efficiency is just how much power it is consuming at a given RPM. And that is for the right graph here. And the differences are a little bit greater. They seem to fall outside of the error bars a lot that the authors give. As a side note, the standard deviation ranges from 0.032 watts to 0.097 watts. And from this figure, it seems like the ridges reduce the power consumed, both for the cicada wing style and the generic drone propeller. So that makes the propellers more efficient because they're producing more or less the same amount of thrust, but with less energy. That's pretty good. And the power reductions are in the order of about 4%. So here we see that we get lower noise and also more efficient propellers, which kind of makes sense because some energy needs to be used to make noise. If you can cut that noise out, you're going to be reducing the energy used for that. Now, comparing the different propellers without the ridges, just as a side note, it shows that the cicada propeller is about 22% more efficient than the DJI propeller, because for the same thrust of 150 grams force, it uses 22.6% less power. So from a purely efficient point of view, the cicada propeller is awesome. Now that is the end of the experimental results. The authors went further with the CFD to see how different ridge amplitudes and lengths, as shown in figure 3a, affect the noise and thrust. So let's zoom down here. Here we go. Figure 3a are the different propellers that they looked at, the different amplitudes and frequencies in inches. Now, as mentioned earlier, the CFD is a little suspect because of the lack of validation and grid-independent studies. So we should just take this as general trends. Now, in figure 3b, we see the effects of these parametric changes for 2000 RPM and 5000 RPM. And for the noise, which is in the top row, blue is better, it means it's lower in noise, and yellow means it's worse, it's higher in noise. And for the bottom row, which is the thrust, yellow is better now because you're getting more thrust, and blue is worse because you're getting less thrust. Now, as a side note, I really like the color bar they used here because while it isn't very visually appealing, it does give the eye a very linear color range. So in other words, a change in color as seen by our eyes lines up pretty well with the quantitative change as well. This results in a more accurate plot as far as when we look at it. Anyway, there is definitely a coupling between the noise produced between the amplitude and the wavelength, because you can see that for this top row here, for both the speeds, 2000 and 5000 RPMs, the changes are not independent of each other. So if you change the amplitude and the wavelength, the value changes in the synergistic effect. So for example, with a wavelength of 0.1 inches, so the bottom left here, and an amplitude of 0.02 inches, we get a local minimum of the noise, this blue part here. But only changing the amplitude doesn't result in the minimum being preserved. So changing the amplitude left or right results in higher noise until we get to another local minimum, of course. So that means that there's this coupling between the amplitude and the wavelength. This makes sense from a tubercle point of view as well, because while we haven't seen how these ridges work just yet, it's likely that they are producing vortices along their zigzag leading edge. And these vortices are very sensitive to the angle of these zigzags. So if you were to increase the wavelength but keep the amplitude the same, then the zigzag would become less sharp, and vice versa. So it makes sense from that point of view that the wavelength and amplitudes are coupled here in terms of their effects on the sound. Now, in addition, the CFD shows that with these different wavelengths and amplitudes considered here, you can get a 2 decibel reduction just by changing the wavelengths and amplitudes to make the ridges more or less prominent. As for the thrust, there are some minor variations, but overall, it shows that the smaller the wavelength is, the more thrust you'll get. That's pretty sweet. And that actually also agrees with tubercle literature as well, because a smaller wavelength results in more lift produced in the pre-stall regime as well. So it's uncanny how these two devices, even though they are supposed to be very different, in fact produce very similar results, and I wouldn't be surprised if they had the exact same mechanism. Let's move on to the flow vis part now in figure 4, because maybe we might see something, maybe not, we'll have to wait and see. So in figure 4 here, in figures 4b and c, let's zoom in here. This is the juicy part. So we see the properties related to the vorticity. In effect, they are showing more or less where the vortices are. That's not strictly true, but it is close enough here. So these figures are for the Cicada propeller, without the ridges. And effectively, the introduction of the ridges produces vortices over the leading edge and the propeller here and the trailing edge. So in that sense, they should work very similarly to our wings in that it breaks up the tonal noise from the leading edge and trailing edges. As for the thrust and efficiency, we can't tell too much from these figures, and in fact, just from these figures, I would be inclined to say that the propeller is actually less efficient with the ridges because the tip vortex seems to be larger whenever you put these ridges on there. But the overall numbers showed otherwise, particularly from the experimental results. So I think we need more information here before we can get a good idea, and perhaps some pressure plots would have been good as well. It would have shown us a bit more. Anyway, in figures 4D and E, we see the dipole and quadrupole strength respectively over the wings in the pressure. In a nutshell, the dipole strength tells us the strength of the tonal noise, so at least one particular frequency, and the quadrupole strength tells us the strength of the broadband noise. It is clear that the addition of the ridges greatly reduces the dipole and quadrupole strengths, especially around the propeller tips at 2000 RPM. So this left figure here, you can see just how much more yellow it is without these ridges. So that tells us why the noise is dropping, at least at this RPM. For 5000 RPM, to the right here, there seems to be more trailing edge noise reduction and not so much from the wing tips with these ridges. However, we need to keep in mind that this is CFD and it may not be that accurate, particularly from what we saw with the setup process and the lack of information there. So that brings us to the end of this podcast, and I was really interested in just how similar these ridges were compared to tubercles. There were so many uncanny similarities. And I was also surprised at just how much more efficient the Cicada propellers were compared to the DJI propellers at least. And perhaps a more thorough investigation is needed to see if this wasn't just at one particular condition. Maybe the DJI propellers are better overall at different conditions, or maybe they're more stable, I don't know. But from this research here, it shows that these Cicada wings are way better so far. And also shows that these ridges were really effective at reducing noise. So it's cool how that effect translates to propellers as well. So finally, if you want to learn how to do OpenFOAM so you can do your own CFD like this or anything else, check out our course and link below. And if you like this podcast, hit the like and subscribe buttons. It really helps us. And peace amigos.